Hi everyone, welcome to the periodicity video. So by the end of this video we're going to be able to describe the trend in the reactions of sodium and magnesium with water, describe the trend in the reactions of sodium, magnesium, aluminium, silicon, phosphorus and sulfur with oxygen, explain the link between the physical properties of the oxides of the elements sodium, magnesium, aluminium, silicon, phosphorus and sulfur in terms of their structure and bonding, and describe and explain the trends of the reactions of the oxides of all these elements with water, acids and bases. Before watching this video, it may be worth watching a couple of Chem 1 videos, especially with regards to this aim here, the third one. So you might want to watch the crystal structure video, and also the melting points video from Chem 1, and that should help us with this. And it's worth pointing out at this point that Chem 5 in particular is very synoptic as a paper, and periodicity is an area where you'll have to think back to your Chem 1 and Chem 2 knowledge. A lot of the time the answers are a lot easier than you would expect, or quite a lot of the time I see students write or trying to think of answers that are more difficult than what the answer is and trying to think too deeply about it. So just make sure that you just put down what's obvious usually. So first off we need to describe the trend of the reactions of sodium, magnesium with water. So sodium Na in group 1 and magnesium Mg in group 2. So thinking back even back to year 10, we used GCSE, we looked at sodium reaction with water, and what happens when it reacts with water is it fizzes, and it fizzes and skims around the surface of the water because hydrogen is being made. So what's being made is sodium hydroxide and hydrogen from the sodium and water. And this sodium hydroxide solution is very strongly alkaline, so you've got a pH of between 13 and 14, and you can make the hydrogen ignite, and it will ignite with a yellow flame because of the sodium burning with a yellow flame. If you compare that to magnesium reacting with water, you firstly can react magnesium with either liquid water or steam. You get different products in each case. If you react it with liquid water, you get magnesium hydroxide and hydrogen. Now that reacts much more slowly than the sodium will. It's a far less vigorous reaction, and this also is far less alkaline, so it's only sparingly soluble, doesn't dissolve very much, and it gives you a pH of around 10 instead. If you react with gaseous water, you get magnesium oxide and hydrogen as well. And this is actually from Chem 2. You learn about group 2 metals and their reactions with water in Chem 2. So moving on, we need to be able to describe the trend in reactions of sodium, magnesium, aluminium, silicon, phosphorus and sulfur, basically the elements across period 3 with oxygen. So we'll start with sodium. So if we burn sodium with oxygen, we get sodium oxide. So this is the equation for it. And sodium burns very brightly with a yellow flame. And it creates that sodium oxide. Magnesium you'll have seen before countless times. You probably see magnesium in year 7, 8, 9, 10, 11 and 12 burning in oxygen. You know it burns with a very bright white flame, and you get magnesium oxide at the end, so it's magnesium plus O2 makes MgO. What's important from these slides actually is that you look at the formulae of the oxide, just so that you don't lose marks in an exam for writing an equation wrong. Those really are marks you'll be picking up every time now. You don't want to be losing those marks. So yes, that burns with a bright white flame and produces that magnesium oxide. Moving on to aluminium, which is actually very reactive, and that will burn very brightly when burnt in oxygen, and it forms aluminium oxide, which is a white powder. So you've got Al plus O2, and aluminium oxide is Al2O3. So to balance that, we need to do the following. And the reason why aluminium doesn't usually react with air is because it has this aluminium oxide layer forming on top of it, which doesn't flake off, so it protects the aluminium underneath. And you learn about that in year 10 usually. And silicon, moving on, needs to be heated quite strongly in oxygen to make silicon dioxide. So the formula for silicon dioxide is literally SiO2. That's all we need to know for silicon. There are two different isotopes of our next one, phosphorus. So there's red phosphorus and there's white phosphorus, which I'll draw in black because you won't be able to see the P. And the red phosphorus must be heated first before it will react with the oxygen, but the white phosphorus is much more reactive. It will ignite spontaneously in the air and give a white smoke of phosphorus pentoxide. And phosphorus pentoxide is P2O5, but it actually exists instead as P4O10, and that's something you need to remember. So to make that, you've got 4 phosphoruses plus 5 oxygens, and you make P4O10. And finally we've got sulfur, which is a yellow solid, and you can't see that. And that'll burn in oxygen to give sulfur dioxide, and it burns with a blue flame. So you've got sulfur plus oxygen makes sulfur dioxide. You get a nice blue flame, and the sulfur dioxide is actually an acidic gas. If that dissolves in water, you'll get an acid, which we'll talk about a bit later. So this is where we come on actually to explain the links between the structures of these oxides and their properties, and basically you're thinking back to Chem 1 stuff. So the first one, sodium oxide that we talked about, that's a metal with a non-metal. So the first thing you're going to think about is its crystal structure, and this is ionic. Now because it's ionic, it has a high melting point. And to explain why it has a high melting point, you would simply say that it has a strong electrostatic attraction between two oppositely charged ions, and because that attraction is strong, it takes a lot of energy to break. The other thing is that it won't conduct electricity when it's solid, because the ions are locked together and they can't move, but as soon as you dissolve it or you melt it, it will conduct electricity, and the ions are therefore free to flow. Now what you'll find in Chem 5 is that the questions are worded slightly different. So in Chem 1 it would simply ask you why doesn't solid sodium oxide conduct electricity, or why does molten sodium oxide conduct electricity. But in Chem 5 what I'll ask you is something like describe a test that you could use to show that sodium oxide is ionic, and what you'd have to say is that when you melted it, it conducts electricity. So you just got to think a bit more laterally when you're doing Chem 5 paper, whereas in Chem 1 you're very much just trying to regurgitate what you've learned and trying to put it on the paper when they ask you a certain question. And that is the difference. The next one is magnesium oxide. Again, this is ionic. You've got a metal with a non-metal, metal being magnesium, the non-metal being oxygen. Again, it has a high melting point because you've got a strong electrostatic attraction between oppositely charged ions, and it will only conduct electricity when it's dissolved or molten, because you've broken the bonds between the ions and therefore the ions can flow. So basically identical to the sodium. Next one is aluminium oxide. I'm sure you can guess what I'm going to say here. So aluminium oxide is again a metal with a non-metal. This is again ionic, high melting point, strong electrostatic attractions in oppositely charged ions, and will also conduct electricity when it's melted or dissolved, because the ions can flow. So you're seeing a trend here. The next one is silicon dioxide. Now the structure has changed here, and this actually has the same structure as diamonds. This is giant covalent, and if you've watched the crystal structure video, you will know that again giant covalent has a high melting point, but the reason you would write is slightly different to ionic. So you'd say that there's many strong covalent bonds you have to break, which requires a lot of energy. This does not conduct electricity in any form because you've got covalent bonds this time, so all the electrons are locked up in the covalent bonds. So what you'd write is that the electrons aren't free to move. So again, just thinking about the information in the crystal structure video about giant covalent molecules and using it in the same way for silicon dioxide. Now move on to phosphorus oxide and sulfur dioxide. So these are molecular crystal structures, and these are held together by van der Waals forces. So when you melt this, actually all you're breaking is van der Waals forces. You're not breaking the covalent bonds that hold the phosphorus and oxygen or the sulfur and oxygen together. You're just breaking van der Waals forces, which are very weak. So these have very low melting points. What you're more likely to be asked to do is compare their melting points. So again, we're thinking back to Chem 1 when you're comparing phosphorus and sulfur. It's just you've got their oxides instead. So remember that phosphorus was P4, sulfur was S8, and so S8 had a higher melting point than P4 because their surface area was bigger. In this case, it's the other way around, if you like. The phosphorus oxide has a higher melting point than sulfur dioxide because phosphorus oxide has a bigger surface area, therefore can create stronger van der Waals forces. So again, just using Chem 1 knowledge, they don't conduct electricity because there's no free electrons. And yeah, the most likely question you're getting asked about these is to compare, if you're thinking about melting points, is to compare their melting points. So now we're going to think about the reactions of the oxides of all these elements with water, acids and bases. We're going to start with sodium oxide, Na2O, and magnesium oxide. Now when these dissolve in water, they form alkaline solutions. Sodium oxide will give an alkaline solution of between 13 and 14, and magnesium oxide around 10. The reason for that is because they both contain oxide ions, so that is O2-, and when O2- react with water, what you produce is two OH- ions. So the O2- ion is very basic and it grabs H+ ions from the water to leave behind hydroxide ions, and hydroxide ions are the cause for alkalinity. The reason why magnesium oxide is less alkaline than sodium oxide is because magnesium oxide is less soluble, and so not as much of it will dissolve in the water. So when you dissolve sodium oxide in water, what you get is sodium oxide plus the water makes Na plus OH minus, and two of each of them, and that's all fully dissociated. Whereas when you dissolve magnesium oxide in water, what you get is magnesium oxide. It reacts with the water to form magnesium hydroxide, and then that's in equilibrium with Mg plus 2OH minus, Mg2 plus 2OH minus. The fact it's in equilibrium means it's not all dissolved. If you react these with acids, then you'll get a reaction. So for example, if we reacted sodium oxide with hydrochloric acid, because sodium oxide is essentially a base, and hydrochloric acid and acid, what you make is salt and water. So you'll make sodium chloride and you'll make water, and then you've got to balance accordingly. So you need two sodium chlorides and two hydrochloric acids. Similarly, if you were to react magnesium oxide with something like sulfuric acid, just do a different acid, then again you will make magnesium sulfate. Remember, magnesium has a 2+ charge, sulfate ions have 2- charges, so therefore you just need one of each to make the formula of magnesium sulfate, and again water, so salt plus water, and in this case it is already balanced. They won't obviously react with bases because they are a base, so there'll be no reaction there. Now if we move on to aluminium oxide, Al2O3, and silicon dioxide, when you try and dissolve these in water, they don't. They are insoluble, which means that they aren't. They don't form an acid or an alkali in water because they just don't dissolve in there. But they will react with acids or bases. In one case, both, because remember, bases don't have to be soluble in water to react with acids. They don't have to be, when they dissolve in water, that's when they're alkalis, but they're bases if they don't dissolve water. So, aluminium oxide, for example, this is an example of an amphoteric compound, amphoteric, and that means it will react with both acids and alkalis. So it's known as an amphoteric oxide. So if we were to react it with, for example, hydrochloric acid, Al2O3 plus HCl, that will form AlCl3 plus H2O, so salt and water, and you need 6 HCl's and 3 waters and 2 aluminium chlorides. So that's it reacting as a base, and then it'll also act as an acid. So if you were to react sodium hydroxide with it, so Al2O3 with NaOH, then you will form sodium aluminate. You also need, water in there as well to balance, and you'll create this. Silicon dioxide is not amphoteric. It will only act as a weak acid with only strong bases. So you have to have hot concentrated sodium hydroxide, which will then react with your silicon dioxide, and it will make sodium silicate. So the reaction there is SiO2 plus 2NaOH goes to make Na2Si O3 plus H2O, and yeah, and that's already balanced. It's worth learning these two reactions, especially these compounds here and here, because they're ones that perhaps you haven't come across before, and therefore those are the ones you're more likely to forget. Obviously, aluminium chloride and aluminium oxide, you've come across these before, so they're hopefully more prevalent in your memory, if you like. But these two definitely worth learning. Finally, we come on to phosphorus oxide and sulfur dioxide. Now, these will dissolve in water to form acids. So, phosphorus oxide will dissolve in water, and that will form phosphoric acid. Sorry, not S. What am I doing? Which obviously readily dissolves in water and therefore creates H+ ions and therefore is acidic. And to balance this, you need four of these and 6 of these. Okay, and then sulfur dioxide will again react with water to form sulfurous acid, not sulfuric, sulfurous, which is H2SO3. That doesn't happen as readily as if the sulfur trioxide, which will probably be created when this reacts with oxygen, which will happen fairly readily, reacts with water to make sulfuric acid, which is what you're more familiar with. So all these are acids because they dissolve in water to form H+ ions when they dissociate. When these compounds react with alkalis, you'll make the salt and water. So I'll just give a couple of examples. So for example, if we had P4O10 reacting with NaOH, you would make sodium phosphate, which is Na3PO4, and water. And you would need 4 of these, 12 of these, and and 6 of those, I think. So again, it's basically an acid plus base makes salt and water, but you've just got to be aware that this is your salt. You need 3 sodiums to go with the phosphate ion. And then if we do the other one, so if we do H2SO3, sulfurous acid, plus sodium hydroxide again, we'll make Na2SO3 and water. We need 2 sodium hydroxides. I'm going to go through quite a few past exam questions now, just to show the range of questions that can be asked on periodicity. So this is the first one, so it gives you a few melting points of a few of the oxides across period 3. So in terms of structure and bonding, explain why sodium oxide has a high melting point. So this is essentially going back to your Chem 1 knowledge, as I was saying in the video. So you need to say that sodium oxide has a giant ionic structure. So there are strong attractions between the oppositely charged ions, and that will get you 2 marks, probably one for the ionic structure and the other one for this explanation, strong attractions between oppositely charged ions. In fact, there may well just be the 2 marks of saying the strong attractions and then the oppositely charged ions, but it's always worth stating the crystal structure first, if anything, just to organise your own thoughts. Part of the same kind of big question, this time it says sulfur dioxide, why sulfur dioxide has a low melting point. So this time SO2 has a molecular crystal structure, so is only held together by weak van der Waals forces. Again, a Chem 1 answer. And then finally, as I said in the video, a question they like, explain why the melting point of P4O10 is higher than the melting point of SO2. So both are molecular, but P4O10 has a bigger surface area, so stronger van der Waals forces. Now this question is very much a synoptic question. It's worth 4 marks, but it still comes under the periodicity topic. So it's state and explain the trend in electronegativities across period 3 from sodium to sulfur. So from Chem 1, electronegativity, if you remember, electronegativity will increase across the period. And the reason for that is there's increasing nuclear charge, decreasing atomic radius, and the same electron shielding. There's your 4 marks. Now this question deals with something that I haven't really dealt with in the video, so I'm going to go over that a little bit later in this question. There's 6 marks for this, so to explain why the oxides of the period 3 elements, sodium and phosphorus, have different melting points. In your answer, you should discuss the structure of bonding in these oxides and the link between electronegativity and the type of bonding. Now this last bit, the link between electronegativity and the type of bonding, is only really worth 1 mark in this question. So we'll first just get through the sodium and phosphorus and the structure and bonding in these oxides. So the first thing you should state is the crystal structure of both. So sodium oxide is ionic, and P4O10 is molecular. So in sodium oxide, there's strong attractions between oppositely charged ions. In P4O10, only weak van der Waals forces holding it together, and so Na2O has higher melting point. Now here there are 1, 2, 3, 4, 5 marks for essentially, again, Chem 1 stuff. Don't be put off by the fact there's 6 marks overall for this question. It's essentially 5 1-mark answers there. Now I'm just going to deal with the link between electronegativity and the type of bonding. So if I just zoom into a different part of the screen, so I just do it here. So if we just draw out the oxides, Na2O, MgO, Al2O3, silicon dioxide, phosphorus oxide, it generally goes from ionic to covalent. Now what makes an ionic compound is the difference in electronegativity. If there's a really large difference in electronegativity, then you'll get ionic compounds. If there's a small difference in electronegativity, then you'll get covalent compounds, with 2 of the same atom joined together being purely covalent because there's essentially no difference in electronegativity. However, when you get to things like aluminium oxide, that has some ionic character and some covalent character, and that's because of polarization. So aluminium, as you go from sodium to magnesium to aluminium, the atomic radius gets smaller, and so what you're creating is something that can get much closer to the oxide ion. So here you've got sodium and oxygen. Okay, here you've got magnesium and oxygen, it can get a little bit closer, but here you've got aluminium and oxygen, which can get really close, and that therefore polarizes this oxygen ion, which then forms some covalent character. So basically, the smaller the ion as you go across the period, the more polarizing it is because it can get closer to the negative ion. So that's why this aluminium oxide has some covalent character. And as you go across from sodium to magnesium to aluminium, more covalent character will be seen. Now if we go back to the question, that last mark is basically, for the simplified version of that, by saying that a big difference in electronegativity leads to ionic bonding, and small difference covalent, and that'll get you that last mark. So again, you don't need to go too complicated here, just putting down the facts will get you those marks. So another one says this question about chemistry of 3 elements, blah blah. Describe what you would observe when magnesium burns in oxygen. Write an equation of reaction that occurs, state the type bonding in the oxide form. Now it's important with these sort of questions you don't write huge lists of observations. It's quite clear that there's 2 marks for the observations, 1 mark for the equation and 1 mark for the type of bonding. The reason being that if you write a list and one thing is wrong, they'll dock marks from you. Just write 2 things that you are confident about. So the first thing you should be confident about is that there's a white flame, or a bright white flame. That will definitely get you 1 mark. The second thing is that it leaves behind a white solid, which is your magnesium oxide. So always think about what the product looks like, because that should give you your second observation. The equation is Mg plus O2 makes MgO, and it's half O2, and the type of bonding is ionic. You've got a metal with a non-metal there. Next one, describe what you observe when sulfur burns in oxygen, and write an equation. So first thing is the flame again. We've talked about it being a blue flame that you see, so you get 1 mark. And then again think about the product. So maybe you write the equation before you start thinking about the other observation. And the product is SO2, which is a gas, and it's a fumey gas. So you could put fumes, you could put a smelly gas, you could put a choking gas. Because it's acidic, that's why it's choking. Type of bonding here is covalent. Now notice they say what type of bonding is there. So that's between the atoms. They're not asking you what the crystal structure is, which is slightly different. The crystal structure is molecular, but the type of bonding between the atoms is covalent. So don't get mixed up between those two things. Next one. State the type bonding in sodium oxide. Explain why sodium oxide reacts to form an alkaline solution added to water. So the bonding, again, is ionic. And the explanation is that the O2 minus ions, so we talked about this earlier, O2 minus ions react with water. That's your first mark. And it's to form OH minus, that's your second mark. So again, don't go too complicated here. Keep it simple. And if you keep it simple, that means you're not spending as much time writing, which means you have more time to read the questions and think about them. Next question, outline an experiment that could be used to show that aluminium oxide contains ions. So here, you could melt it, and then if molten substance conducts electricity, it contains ions. Now it's important here, there's a couple of things to think about. Because it's aluminium oxide, we can't say dissolve it in water, because as we've said before, it does not dissolve in water. It's insoluble, and therefore that couldn't test for it. So you have to melt it, and I think with ionic compounds, I wouldn't take the chance, just always melt it, because they can always be heated and melted. They can't always be dissolved in water, so always go with melted when you're outlining experiment. And the second thing is to say, don't just put see if it conducts electricity, because you're not saying what the positive outcome of that would be. So if you say see if it conducts electricity, and if it does, then it's ionic, or it contains ions, then that'll be fine. So you've got to say what the outcome of the experiment would tell you. You can't just say see if it does this, because you're not actually saying what you need to be able to see. I hope that makes sense. Next question, suggest one reason why a thin layer of aluminium oxide protects aluminium from corrosion in moist air. So there's a few things you could say here. First thing, that it's insoluble. So aluminium oxide is insoluble, so that would get you the mark. Or you could say that it's inert as well, and that would also get you the mark. Next one, write an ionic equation in each case showing aluminium oxide reacts with the following. So an ionic equation. So you're only showing the ions that are reacting. Now, aluminium oxide, as we've said, is not soluble. Therefore, you can't write out the ions separately. If it's not soluble, then it's not going to have ions in water. But HCl is soluble, and the Cl minus ions are not. Well, they're spectator ions, and what you'll form is Al3 plus 3H2O. So you form aluminium chloride, but that is ionic, and that will dissolve in water, so the chloride ions are spectators. To balance, you need 2 of those, 6 H pluses, sorry, and 3 waters. So this next one is aqueous sodium hydroxide. Again, you're starting with Al2O3, because it's not going to separate into its ions in water, it's insoluble. And this time, the sodium hydroxide does dissolve in water, but the sodium ion is going to be a spectator ion, so we only want hydroxide ions. And remember, with this reaction, you also have water. And what you create is this molecule, NaAl, if you were doing the non-ionic version anyway, OH4. But because the sodium is a spectator ion, all you're going to make when you're drawing the ionic version is AlOH4 minus. And then you've got to balance it. So that's 2 of these, 2 of those, and 3 of those. Now this final question is a mix between periodicity and moles, and there's generally a question like this in every Chem5 paper. It doesn't always link to periodicity, it sometimes links to redox well, it's either going to be redox reactions or periodicity. I suppose they could link it to complex ions, because you could have equations and reactions with the DTA and things like that. Basically, if there's equations involved in the topic, then they could use that as this sort of question, because the equation's the important bit and it's the bit you should always start with. And then once you've got the equations, it becomes just a standard moles question with a bit of a difficult bit at the end. With this sort of question, you want to extend Mr. T to E Mr. T, because you always want to start with what the equations are. So let's just read through the question. It says a chemical company has a waste tank of volume 25,000 decimeters cubed. The tank is full of phosphoric acid, formed by adding some unwanted phosphorus oxide to water in the tank. 25 centimeter cube sample of this solution was required. Sodium hydroxide solution was a complete reaction. Calculate the mass of phosphorus oxide that must have been added to the water in the waste tank. So the first thing to do is just write out the equations. So the first equation here is the adding of the phosphorus oxide to water to create the H2PO4. So you got P4O10 plus H2O, and that makes H3PO4. And then you just need to balance that. So you've got 4 H2PO4 and 6 waters. There is another equation here. It says that there's a titration of sodium hydroxide with this solution. So the other equation I need to write out is H3PO4 plus the sodium hydroxide makes sodium phosphate and water, and then you just need 3 waters and 3 sodium hydroxide. So now we've got our equations, so we've done our E bit. The next bit is M in Mr. T, so there's always a way of working out the number of moles of something in one of our equations, and here we've been told that the sodium hydroxide solution needed, this is how much is needed, so we can work out moles sodium hydroxide. Now with these sort of questions where there's a lot of calculations and a lot of working, I would always label my numbers. So moles of NaOH will equal 21.2 times 0.5 over 1,000, and that equals 0.0106. And then you can use ratio to work out how much phosphoric acid is to react with that. So moles of phosphoric acid equals 0.0106 divided by 3, which equals 0.00353.
And then we just have to consider that the titration has used 25 centimetres cubed of the original 25,000 decimeters cubed, which was in the tank, which is a multiplication of 1,000,000.
So what we need to do is multiply this number of moles we've got by 1,000,000. So we've got moles of H3PO4 in the tank equals 0.00353 times 1,000,000, and that equals 3,530. From that, we need to use a ratio, again, of this first equation that we wrote, and we need to work out how much phosphorus oxide was used to make this much phosphoric acid. So our moles of P4O10 will equal 3,530 divided by 4, as per the ratio, which equals 882.5. Then we need to work out what the question asks us, and this is where the triangle comes in of our Mr. T, work out the mass. So mass equals moles times MR. So moles times MR equals 882.5 times 284, which is our MR of the phosphorus oxide, and that gives us 250,630. Now remember, our MR values are in grams, and if we look back at the question, our final thing is that the question wants the answer in kilograms, otherwise you won't get that final mark. And so we need to divide our answer by 1,000, and that gives us 250.6 kilograms.